Hi, it's Mrs. Allison. Today we are going to look at 5.1a. And to start, let's begin with the warm-up. All right, hopefully you had a chance to look at the warm-up, and I will tell you that the answer is D. So let's talk about why this answer is D. If you recall, when we have a derivative of an integral, they undo each other. But the problem is we have a function in here, this x cubed, that when I plug it in, and if I plugged it in and then took the derivative, I would have a chain rule. And so the derivative and the integral undo each other. So the primary function is still this tangent of something to the fourth minus 1. But what's going to be in place of that something to the fourth is going to be that x cubed. So tangent of x cubed to the fourth minus 1. And then we'd have that chain times 3x squared, which is where we get D. All right, let's talk integration strategies. All right, so some of the strategies we've looked at so far, let's talk about those. First, we have our simple integration that we've looked at. You know, simple integration like, oh, the power rule. Or maybe our favorite rule, which is e to the x. Or maybe our simple trig, like our sine and our cosine functions. We can find those antiderivatives pretty easily. All right. Second, what did we look at? Most people go to use substitution, and that's correct because that's like the chain rule of integrals. And so then that would be the next progression is our use substitution. Now, think back to some of the other ones we've looked at. Most recently, we looked at long division, using long division to be able to take the antiderivative, which ended up with some algebraic work. And maybe we would include in there the logs and exponentials that we used with the long division. Those come into play too. Now, there are 3 new strategies that we are going to talk about over the course of this chapter. And the first strategy we're going to talk about is something called integration by parts. You may see it abbreviated IBP by me. I don't know that it's abbreviated that way by anybody else, but integration by parts is what we're going to focus on today. Then we are going to look at integrating using trig identities. And finally, our last technique that we're going to talk about is what we call partial fraction decomposition. And we'll work on that a little bit later. So let's get started with integration by parts. Okay, we know how to differentiate a product. But what about taking the integral of a product? So let's start with the formula for the differential of a product. We know that if we have y equals u times v, and I want to take the derivative of y with respect to x, it means that when I take the derivative of u and v, it's going to be an implicit differentiation. So it is a product rule, so I would do the derivative of u with respect to x times v plus the derivative of v with respect to x times u. And yes, u and v can get a little bit confusing, but typically those are the variables used for integration by parts. So maybe just put that little tail on the u as you write it. Now, do you agree, since they all have the same denominator, they all have that same differential of dx, we know that if I have an equation where every term has the same denominator, then I can just basically ignore the denominator. So let's ignore the denominator, but let's rewrite this function. So dy equals v du plus u dv. It's more in the format we're used to seeing it. And now I'm going to integrate all sides. Now, I can do this to the left-hand side and the right-hand side, but since it's a sum with two different differentials, I'm going to include it as two different integrals. And doing it this way, I get that dy, the integral of dy is just y, but the problem is I don't really know enough about these two integrals to say anything. Now, I'm going to reorder this. I'm going to reorder this so that I get the integral of u dv equals y minus the integral of v du. So just some algebraic manipulation. And you'll notice that this variable y right here is equivalent to u times v, and so I can rewrite this to say the integral of u dv equals u times v minus the integral of v du. This is the formula for integration by parts. So if u and v are differentiable functions, then the integral of u dv is equal to u times v minus the integral of v du. Now, a couple of things to note. We're going to have to choose two variables. We're going to have to choose two expressions, u and dv. And this will make more sense when we go through a couple of examples. But some helpful strategies are that I want to choose u so that it's easy to differentiate it. And I want to choose dv so it's easy to integrate it. Now, more than just easy to take the derivative and easy to take the integral of, I want the results to be also as nice as possible. Okay, so let's look at an example. All right, so let's look at this first example. I went ahead and rewrote the integration by parts formula up at the top so you could see it. Now, in each of these boxes, you'll notice that I have two sections highlighted. I have u and dv highlighted on all of them. That's because in each time when we start, we're going to find or define a u quantity, and we're going to define a dv quantity. And that's how we build integration by parts. Now, I'm not always going to give you a table like this, but if we can keep our thoughts as organized as possible, it makes it easier when we go to substitute into the formula. All right. So in this particular example, I'm going to let u be the expression of x. And I'm going to let dv be the expression cosine of x dx. Now, why, you might ask? Yes, it is true that both of them are easy to integrate and easy to take the derivative of, but in taking the derivative of u, I get the most simple expression possible. Let's look at that. Normally, when we take the derivative of this expression, u equals x, with respect to x, we would have to do it implicitly. And so we would get an expression that says du dx equals 1, because the derivative of x is 1. Now we're going to write it in its differential form, and so therefore we're going to say du equals dx. Okay. Now I'm going to take the antiderivative, meaning I'm going to take the integral of both sides. I probably won't write this ever, but just so you know, this is what we're doing. And so when I take the integral of both sides, we know the antiderivative of cosine of x is sine of x, and the antiderivative of dv is just v. So now all I need to do is take these pieces that I have and substitute them into this formula. So my u is x, my dv expression is cosine of x dx, and the rest of it is going to go into the formula. So u is x, v sine of x, minus the integral of sine of x du, which is just dx. So this is my integral. Now I'm going to integrate this second part here, this sine of x, but notice the integral became a lot easier. I can take this antiderivative. So I get x sine x minus, well, the integral of sine of x is negative cos x. And the one thing that I cannot forget that this needs a plus c because it's not a definite integral. We don't have bounds, so I need that plus c. So we get x sine of x plus cosine of x plus c. There is my antiderivative. Now, if you wanted to, you could certainly go and check your work, and I don't think it's a bad idea to do that. So if we were to check our work here, we would go and take the derivative of the expression we just found. And if we take the derivative of the expression we just found, we would expect that the answer I get is x cos x dx. So let's do that. This would have a product rule, so I'd do the derivative of the first times the second plus the derivative of the second, well, the derivative of sine is cosine, times the first, minus, or times the, or plus the derivative of cosine of x, sorry, which is negative sine of x, and the derivative of c is just 0. And simplifying this, we get cosine of x times x. And you can see that we're back to what we started with originally, so I know this is the antiderivative. Okay. So hit pause and try example number 2. Let's see what you can do. All right, hopefully you had a chance to try number 2. Now, what I'm going to do here is I'm going to let u be x, and I'm going to let dv be e to the x dx. And if I take the derivative of u and x, I get du equals dx. And if I take the antiderivative of this dv expression, I get v equals e to the x. And again, you might wonder why we go in this order. But if we try it the other way, eventually we'll get the right answer. It just may take more work to get there. So this integral is equal to u times v minus the integral of v du. And I know the integral of e to the x. So we get x e to the x minus e to the x plus c. How'd you do? All right, try example 3, which is a little bit different. So hit pause and come back. All right, looking at example 3. What did you let u be? What did you let dv be? Well, it's kind of funky, this problem, because there's really only appears to be one expression. So I'm going to give you a scenario, and then I'm going to erase it. So just watch. If I let dv be the natural log of x dx, then it means I need to find the integral of the natural log of x dx. That's the very problem we're working on. So this doesn't change, doesn't help me create parts at all. So this is not right. So instead, I'm going to let u be the natural log of x, and I'm going to let dv just be dx. And because I can take the derivative of the natural log, and I get 1 over x dx, and I can take the antiderivative of dx and just get x, or v equals x. And so then when I take the antiderivative of the natural log of x, we get x natural log of x minus the integral of x times 1 over x dx. Simplifying, we get x natural log of x minus the integral of dx. Well, the integral of dx is just x. And there's my expression. You might wonder, we never really looked at the antiderivative of the natural log before. Even when we did that whole section on logs and exponentials, we left off the integral of the natural log of x. And this is why. We didn't have the techniques to be able to understand where it came from. Sure, I could have just given you the formula, but it doesn't help in understanding where it comes from. Now let's look at definite integrals. When we look at a definite integral, I'm going to start the problem the exact same way. In fact, I'm going to ignore my bounds of integration until I get that antiderivative. So until I complete the integration by parts, I'm not touching those bounds. Okay, so in this problem, I'm going to let u be x and dv be e to the negative x. And if you're feeling brave, hit pause and come back and check the answer. Otherwise, let's follow along. So I take the derivative of u and the derivative of x, and I take the antiderivative of e to the negative x. Oops, this should have had a dx, which would be negative e to the negative x. So u v, I'm going to stick that negative out front, minus the integral of v, got another negative in there, du. So I'm just going to simplify this because I think it'll make it easier. Okay, I've already done this antiderivative. We've done it right here with dv, so I know this antiderivative is negative e to the negative x, and normally at this point we'd put a plus c, except this is a definite integral. And what I need to do now is evaluate the entire expression, not the part that just had the integral here, but the entire expression, because the whole thing represents the integral from 0 to 4 of x e to the negative x. So I'm going to evaluate this. So we would get negative 4 e to the negative 4 minus e to the negative 4 minus, and then I'm going to substitute in 0. So we get negative 4 e to the negative 4 minus e to the negative 4 minus negative 1, because e to the 0 is negative 1. I can combine these, so we get negative 5 e to the negative 4 plus 1. And there's my definite integral. All right, hit pause. Try this last one and see how you do. Okay, so on this particular problem, I would let u be the natural log of x. So du would be 1 over x dx. And dv I would let be x cubed. So v would be 1/4 x to the 4th. So it's a little bit messier, this one. All right, so u, v, so 1/4 x to the 4th natural log of x minus the integral of v, oops, that's not an e, v du. And I'm going to simplify this integral before I take it. So I've got 1/4 x to the 4th natural log of x minus 1/4 the integral of x cubed dx. So I'm going to go up a degree, divide by that degree. I already have a negative 1/4 out front. This I'm just going to rewrite a little bit simpler. So my antiderivative before substituting in my bounds of integration looks something like this. And I'm going to evaluate the whole thing from 1 to e. So e to the 4th over 4 natural log of e minus e to the 4th over 16 minus, now substituting in 1, okay, combining like terms. Let's see. Natural log of e we know to be just 1, so this would be e to the 4th over 4 minus e to the 4th over 16 minus natural log of 1 is 0, so this expression goes away, leaving me with 1 over 16, negative 1 over 16. And so combining like terms, I mean, we could leave it as e to the 4th over 4 minus e to the 4th over 16 plus 1/16, but chances are on an AP test, if this were a multiple choice question, this would all be combined. So finding common denominators, I would multiply this by 4, so 4 minus 1 gives me 3e to the 4th plus 1 over 16. How'd you do? So this technique is integration by parts. And there you go.